Hi, I'm John, and this is my video about containerisation. In this video, I'm going to be talking about containerisation and giving a brief overview. I'm going to start by giving some context around some of the approaches we have for running our applications, some more traditional and some more modern. This includes physical servers, virtual machines, and containers. We're then going to have a closer look at how containers work, and this is in the context of the Linux operating system and the Linux kernel, and how containers are virtualized on top of Linux. We're then going to compare containers to virtual machines and explore some of the reasons why we would choose containers over a more traditional virtual machine approach. Finally, we're going to explore a Docker file, and a Docker file is the file that defines the process for building a Docker container. So I want to start by giving some context around some of the methods we've had in the past of running our application. In the 1990s and 2000s, it was pretty typical that a business would have a physical server that ran in their server room or data center, and on top of that physical server they would install the operating system, and on top of that operating system they would install an application. This meant that there was one physical server dedicated to an application. If the business then wanted to deploy another application and make use of another application to serve a different business need, they would need to purchase another physical server. On top of that physical server, they would need to install the operating system again, and then they would install the application. So this was pretty typical in the 1990s and 2000s, and for obvious reasons, this was very inefficient, expensive. The time to get an application deployed and ready for use by users was typically a long time waiting for us to procure that hardware, set it up and install the application. This then led us on to virtual machines, and this is a generational leap in the way that we could run our applications and machines, which became mainstream by the 2010s. So virtual machines virtualize the hardware of a computer. A virtual machine has a operating system just like a physical machine, and for all intents and purposes, virtual machines and the operating system within them don't know that the virtual machines and they act exactly as the operating system would on a physical server. And this is facilitated by what's called a hypervisor. Some example companies or products that provided virtualization were VMware and Microsoft Hyper-V. VMware was the market leader in virtualization and the most popular with a lot of businesses. They provided the free virtualization software hypervisor called VMware ESXi. They then had more advanced virtualization technologies on top of that. So if we look at the diagram here, we've got the infrastructure. This represents the physical servers. On top of the physical servers, we had the hypervisor software installed, and this is the VMware or Hyper-V that would facilitate the virtualization, virtualize the hardware for the virtual machines, manage, start, stop, and coordinate the virtual machines, or provide an interface for us as admins to go in and modify the virtual machines. So then on top of the hypervisor, we have the operating systems, and you can see here, if this diagram represents one physical server, we have 3 guest operating systems running on top of that physical server, thanks to virtualization and the way that it virtualizes hardware. So 3 separate operating systems, and each has the full OS, kernel, and resources. They're isolated thanks to having their own kernel, just as physical servers would. And this approach worked very well for many years. It does have some inefficiencies now. The storage of a virtual machine typically uses 60 gigabytes. So we're still talking about using 60 gigabytes plus, because it can be more as well. 60 gigabytes plus per application, and this provided still some inefficiencies. This leads us on to containers, and containers now are an even more modern approach than virtual machines, and they provide another layer of virtualization. This time they virtualize the application on top of the same OS. So looking at the previous diagram where we've got those guest operating systems, we've still got one application per operating system there. Now, as we look at containers and we look at this diagram here, we've got the infrastructure operating system, that could be a virtual machine operating system, a container engine, which is an application installed on top of the operating system and is used to manage the containers. An example would be the Docker engine if you're using Docker, which is the most common containerization technology. And then on top of the container engine, we're running 3 different apps here. So whilst the same OS is being used, these applications are completely isolated, and this is facilitated by the operating system and the container engine. So ultimately, it allows multiple applications to run on top of the same OS in isolation, and these are lightweight, standalone executable software packages. So containers are referred to as standard units. In this standard unit, we've got all of the components are our application defined. This can include dependencies such as certain frameworks, and they do share the same OS kernel, although they are isolated using mechanisms of the Linux OS kernel, which I'm going to get into in the next slide. We have low latency between containers on the same or nearby hosts, and ultimately the OS is virtualized for a container. So where virtual machines, the hardware was virtualized, for containers, the operating system is virtualized. As far as the container is concerned, it's got the operating system to itself. It's running on top of a virtual machine effectively, and it has no knowledge of the other applications running on that machine. So now I want to get a little bit more into how containers work and how that isolation is provided in the operating system. So a key feature of the Linux kernel that's used for containerization is namespaces. And this allows one set of processes to see one set of resources from a different set of processes. These are some of the namespaces that provide isolation. So we've got process ID, and this means that processes in one container can't see the signal processes in another. The network namespace provides each container with its own network stack, IP addresses, route tables, and network devices. Then the mount namespace, which ensures processes in one container can't access the file system outside of their namespace. Inter-process communication prevents processes in different containers from communicating through IPC mechanisms. And Unix timeshare, which isolates host name and domain name. Each container has its own host name, just like a virtual machine would. So ultimately, this feature of the Linux kernel is one of the core components of the kernel that's used to virtualize the application. Next, we have the container engine. So a good example of this is the Docker engine, and this is what we install on top of the operating system where we want to run Docker containers. And the container engine manages container images, which are the blueprints for containers. They pull and push images to container registries. They're responsible for creating, starting, stopping, restarting, and deleting containers. They manage network aspects, including network interfaces, IP addressing, and port mapping and forwarding. Storage as well, providing a layered file system, handling volumes, persistent storage, logging, capturing logs from containers, and integrating with external logging solutions. And they also provide a CLI to allow users and administrators to interact. So they act as a front end to the user, providing a CLI for us to interact with the container engine. So this example is container. It's Docker that contains the CLI capability. So finally, why would we choose containers over a more traditional approach? Well, containers provide the benefit that they have very fast startup times. So typically our operating system where we're going to run our container is already running. In a virtual machine where we've got a virtual machine and we've got our application installed on top, we start the virtual machine, it might take a minute or two for the operating system to start up, and then we've got to wait for services to start up and then the application. So there can be a period of time where the users can't access the application because it's not up yet. Containers can typically get running within seconds, and they're very fast, thanks to us not needing to wait for the OS. Though containers, of course, are still dependent on the OS still needs to be started. But if the OS is already running, we can kick off a container within seconds. It will be up and running and ready to receive requests from users. Another benefit is consistency across environments. So a common problem we have with virtual machines is that over time, between different environments, they begin to drift apart in their configuration. In dev environments, we typically got less governance. We're more inclined to do quick fixes, quick changes, and over time, this becomes drifted and not representative of production anymore. This is in contrast to containers, where we have in a container, we define a process for what needs to happen to build the Docker container, and we can use that exact same configuration in dev, test, and production. So it can help resolve a lot of those issues that we can have with configuration drift with more traditional virtual machines. Automated orchestration using platform tools like Kubernetes. So Kubernetes is a separate product that can orchestrate containers. It will have a number of nodes. It will run containers on top of those nodes, and it provides orchestration. So if we've got a microservices architecture, which is where we've broken down different components of our application into smaller parts and containers, we can have Kubernetes, say for one container, it notices for that single responsibility that one service is on the high load, so it can scale up automatically, and it can scale down. So it's an orchestration service, and this is one of the benefits of using containers, is we can use tools like that to very efficiently use the hardware. It naturally supports microservices architecture. So as I mentioned, microservices, a modern approach to application architectures that's becoming very popular, and containers are very supportive of microservices architecture. They are a mechanism that we can use to break down our application and the services of the application into small parts. They're also supported over fast and frequent and reliable releases with CI/CD tooling. So modern approaches with DevOps and how we can build and test and deploy our application, we're often aiming to do that frequently, several times per day. And the use of containers and the speed and the mechanisms and the way that we have a standard unit is very supportive of those modern DevOps approaches. We've then got it's kind of an expansion of the configuration drift. It should run on a variety of system types, local PC, on-premises, and public cloud with little or to no modification. So that in the example of Docker, we've got a Docker file, same process for building a container, and we run it on our local PC, on-premises, and public cloud in the exact same way. There may still need to be some modification, but typically very close and very different to a virtual machine where we deploy our application to a virtual machine, and there can be differences quite easily due to the scope of configuration that we can change on a virtual machine. Finally, we've got a strong ecosystem, including a number of tools, extension and community support. So it's an open source product. We've got a lot of support, and with containers growing maturity and popularity, there's a lot of community support now. So finally, I'm going to look at a Docker file. We're going to kind of have a look through a Docker file for a .NET application and explore some of the things that are defined. So the Docker file is used for the build process of a Docker container. Once we've developed our application, we will generate or write a Docker file like this, which defines the procedure of building the application within the container. We run Docker build. Once that succeeds, so if there's no issues, we can then publish it to a container registry, and then our container engine can then pull it from the container registry. So our mechanism is always build the application, publish it to the container registry, and then when we're ready to run that application in different environments or production, we can pull from that container registry. So if we look more closely at this example of Docker file, we've got the top from MCR Microsoft.com.NET ASP.NET 7. So we're basically saying here that the base image for our Docker container is ASP.NET 7. We're then switching the working directory to /app, and then we're telling container using the expose commands that this application is listening on port 80 and 443. We then have from, and at the end there you can see that we've got build, and this triggers the build command. So these commands here, we've got further down restore, build, publish. These are native commands to build in a .NET application, so these are specific to .NET. If you're using a different application and containerizing a different application with different framework, programming language, the commands are going to be different, but this is an example of .NET. So we've got a working directory, which again changes the working directory. We're copying the CS project file, which is the core project file in a .NET application, to a specific directory in the container. We're then doing .NET restore. We're then copy ... is copying the entire contents of the current directory from the local machine into the container. We're then changing the working directory. We're then doing .NET build, and then we are building again on top of that and doing .NET publish. So these represent the different layers of our Docker container. And finally, we've got the finalization and the publish. This concludes my presentation on containerization. Thank you for watching.